Hey everybody, I'm Chili. Welcome back to Advanced C++ Tutorial 4. Today we're talking about rotation. Now, rotation is one of the most important topics on our journey to understanding 3D graphics, and it's also super useful in 2D graphics. So we gotta keep it serious today. We gotta treat this topic with the gravitas that it deserves. Now, the first thing we should note about rotation is a decidedly circular phenomenon. Let's say you're rotating your arms around in windmill fashion. It doesn't take much imagination to see that your hands are, tracing out circles. So to study rotation, we need to get to know circles, and I'm talking in the biblical sense here. Now, if we're talking circles, we should also be talking angles. I mean, we all intuitively understand what an angle is, but let's give ourselves a nice concrete definition of an angle and also how angles relate to circles. Obviously, angles relate to rotation, right? Because, an angle is the unit that is used to specify the magnitude and the direction of a rotation. Now, when people think of angles, they maybe think of something like this, something pointy like this, and you mark off the angle. There's a little symbol for it. You put the little arc right in there, and you say, this is the angle. It's right here. See it? That's an angle. Let's rewrite this a little bit. Let's make it a little more general and mathematic. So let's change it from a pointy corner into two general lines here, and then the angle between them is going to be, right around there. Now, if I were to say, guess this angle here, you might give me a number something like, that looks like around 27 degrees. But what does that mean and where does it come from? Well, let's draw a circle, unit circle, at the center of where these lines intersect. So the center of the circle is the center of intersection between our two lines that form the angle. Now, if we draw an arc from one line to the other here, this arc, as a percentage of the whole arc of the circle, that is the angle. That's what an angle is. It's the percentage of arc with respect to the entire circle. And this turns out to be a good way to measure angle, because if you just measured the distance between, two corresponding points on these lines, your measurement would change depending on where you measured it. But measuring it as a percentage of arc of the circle means that no matter where you measure it, no matter how big this circle is, it's always going to be the same percentage of the entire arc. Because as the circle grows, the circumference also grows at the same rate. They're both linear. So here, no matter what circle you use, as long as it's centered at the point of intersection, the angle, the arc that's used to measure the angle, is going to be the same percentage of the entire circle. So in other words, what an angle unit means, it means go some percentage around a circle. So this angle here might be something like, 8%. But that's not how we talk about angles, is it? We usually talk about angles in terms of degrees. So we might say this is, like 27 degrees. What is a degree? Well, degree, the whole circle is 360 degrees. So a half circle is 180, and quarter circle is 90 degrees, etc., etc. So it functions the same as a percentage. Instead of saying 50% of the circle, we say 180. But why do we choose this weird arbitrary 360 to represent a full circle? Where's that shit come from? Well, it actually comes from the ancient Sumerians. You see, these guys thought they were pretty damn smart. So unlike most human civilizations which settled for a base 10 number system, because, we have 10 fingers, they decided, we're going to go base 60, baby. So you know how base 10 is decimal and base 16 is hexadecimal? Well, base 60 is, I shit you not, sexagesimal. And if that isn't just the dirtiest shit, I don't know what is. So so that's why we have 60 seconds in a minute, 60 minutes in an hour, and it's also why we have 360 degrees in a circle, because, 60 times 6 is 360. It all fits together. So basically, there's no real imperative to use 360 for the number that represents a full circle. It's just how we've been doing it for literally thousands of years. Just an arbitrary human choice. Now let me give you a better non-arbitrary alternative. So let's say instead of going halfway around the circle is 180, let's say halfway around the circle is 3.14159 ... It keeps going on. It's an irrational number, so you can't actually write it out perfectly. So in general, we just like to represent it with a little symbol that looks like this. You may have heard of it. It's called pi, right? So pi, let's say that pi is the number we want to represent halfway around the circle. So the full way around the circle would be 2 pi. Now you might be saying, Chili, I understand that 360 is a bit of an arbitrary bullshit number, but if that's an arbitrary bullshit number, this is just plain fucking retarded. But it's not retarded. It's actually super smart. So if we look at our circle here, the radius of the circle, we could draw it right here, is 1, right? Now let's take that radius, that distance of 1, and lay it out along the circumference of the circle as if it were like a piece of string. So I'm just going to eyeball it here, but let's say that this is about 1 radius. Here, we got 2 radiuses, 2 radii. Here, 3 radii. And here, what you'll have left here is 0.14 radii. So if you take the radius and you lay it out along the circumference like this, you will go exactly 3.14 times your radius along here to get to the half circle. And that, my friends, is the true meaning of pi. Pi is how many radiuses it takes to go halfway around the circle. And this number is the same no matter what size circle you have, because the radius grows at the same rate as the circumference when you make a bigger circle. So now we can define the angle, the percentage of arc of a circle, in terms of the circle, in terms of its most fundamental property, which is its radius. And that turns out to be super good for lots of math bullshit. So this is the smart person's way. This is the civilized way of talking about an angle. We call this unit, we say we're talking in radians, right? Because it's part of the radius, right? How many radiuses do you go around the circle? That's your radians measure of angle. Degrees are for the uncivilized, unwashed masses. And if you use degrees, you are a savage. Don't at me. Radians are the civilized human being's way of talking about angles. Don't at me. So if we want to talk about an angle that goes, 1/4 away around the circle, we don't say 90 degrees. Nah, we say pi over 2. 1/8 of the way around the circle, obviously that's pi over 4, half as much as pi over 2. And so on and so forth. We generally like to talk about degree or radians in terms of fractions, although you could just, give numbers, but they're not that good to look at, really. We like to stick to fractions for the most part. But yeah, this is how we are going to be talking about our angles. This is also the unit of measure that the standard library uses for things like sine and cosine. So if you can't think in terms of radians, you're constantly going to have to be converting between radians and degrees in your code, and you're probably going to mess it up somewhere. It's dumb. Just use radians, which is what I would like to say. But whereas a lot of libraries, especially math-related libraries, use radians, some libraries use degrees in order to appease the unwashed masses. I mean, looking at you, SFML. So if you're, say, using SFML together with Box2D, Box2D is a sophisticated man's tool. It uses radians. SFML is a tool for babies. It uses degrees. You're just going to have to deal with it. All right, now let's change gears and talk about trigonometry. Trigonometry. Try to pay attention because this shit is kind of a big deal. But don't get triggered by all the math bullshit. No, but seriously, trig means triangle, right? And metry means to measure. And no means no fucking way you're gonna understand 3D graphics without learning this bullshit. You got it? Okay, now forget all that bullshit. because I'm going to tell you the biggest kept secret of the junior high school education world. And that is that trigonometry doesn't actually have anything to do with triangles. It's all about the circles. Remember, I said we're talking about circles here. Trigonometry is about circles, which is awesome because circles are way better than triangles. Everybody knows this. Well, let's say we got a unit circle and we got a line that is going through the origin. It's intersecting the circle. That line makes an angle with the positive x-axis. We call that angle theta because that's what we usually call our angles. And it is going to intersect with the circle at some point. And I'm going to ask you, what's the x and the y of this point? What are the coordinates of this point here? And you're going to say, I don't know, Chili. Ask somebody who cares. Well, that was a very churlish response. You should be ashamed of yourself. The answer to this burning question is the x is cos theta and the y is sine theta. That is the meaning of cos theta and sine theta. They give you the x and the y coordinates of a point on the unit circle corresponding to some angle. So you give them an angle that represents basically this line here, and it will tell you the point of intersection on the unit circle. This is why, if you know anything about cos and sine, this is why cos theta and sine theta are always they're between 1 and -1. Because look at the unit circle here. The coordinates all fall between 1 and -1. So to hammer the point home a little better, I've got this interactive applet. You can check it out here. And it allows us to rotate this point on the unit circle, give it a particular angle. We've got the angles marked out here. And it will tell us the x and the y coordinates of that point. You see it's drawing it here as a nice little triangle, which is, where the whole trigonometry thing comes from. But it's definitely tracing out a circle here. And you can see here that the values are just the values of sine and cos of the angle. There's also tan. Don't worry about tan. Nobody likes tan. Doesn't get invited to any parties. Sine and cos are where it's at. And here we can see that as we trace out the angle going 360 degrees, if we use that as the horizontal axis in a graph, we can see that our sine and cos just trace out the familiar sine and cos lines that we're used to. Now to separate the civilized human beings from the savages. There's something wrong with this diagram. Can you tell me what it is? Of course, it's in degrees. That's just those dirty Sumerians again getting at us with their sexagesimal. No, we like radians. This is what it looks like with radians. Here you can see pi over 6, pi over 4, pi over 3, pi over 2, all the good stuff, all those fractions. Everyone loves, you guys love fractions, right? We all love fractions. All right, so that's sine and cos. They're just these little magical functions. You jam in an angle and they will poop out some coordinates for you on the unit circle. Now there's two more functions that I should go over here, and they're called arcsine and arccos, and they're often written like this: sine to -1, cos to -1. And what these guys do is they do the opposite of cos and sine. They undo them. They are the undoers. So for example, for arcsine, you give it a y coordinate and it will tell you the angle that is used to produce that y coordinate. Now the funny thing about arcsine and arccos is that there is not one true answer for this. Like for example, so let's say I give you a value and I say this is the y coordinate on a circle, and I want you to give me the angle that corresponds to that coordinate. And you say, okay, well, this is the y, then the angle must be here. It must be this theta. So sine -1 of, let's say this is 0.6, sine -1 of 0.6 is going to be, theta, whatever this theta is. But there's a problem with that, right? Because that's not the only angle that can produce this y. This angle here, so if I draw a little line from here to here, this angle could also produce that y. We'll call this angle phi. So there is not one conclusive answer when you take the arcsine. There's going to be multiple possible answers, because it could be theta, it could be phi, it could be theta plus 2 pi, or theta plus 4 pi, or phi plus 2 pi, right? However many times you go around the circle, you end up at the same point. So there are actually infinite number of solutions. In general, what we do is we declare the range for arcsine to be between pi over 2 and negative pi over 2. And in this range, it is unique. In this range, for 1y, you only have one solution here. Only one solution here. So that's what you do. And sine negative 1 is to basically undoes the work of sine. It is the inverse function. And it's the same for arc cos, only arc cos runs from 0 to pi. Because again, in the range of 0 to pi, this range here, given any x, you're only going to have one solution, one solution, one solution. But yeah, cosine takes angles, it poops out a x-coordinate. Sine takes angles, poops out a y-coordinate. Arcsine takes a y-coordinate, and it poops out an angle. That's the difference. Mostly we use these guys, but sometimes these guys can be useful. Alright, so we know how to use sine and cos. We know that if we're given an angle, theta, we can find a point, x and y, on the unit circle. But what about the non-unit circle? What if I'm given an angle, and we'll call this angle phi. You write phi like that, sort of. And I want to find a point on a non-unit circle. How do I do that? It's not going to be the same result, obviously, as just sine and cos. What's the difference? Well, I mean, if we find the point on the unit circle, it's going to be right here, right? So it's just going to be cos phi, sine phi. Now, the point on the non-unit circle here, it's the same angle. What we're really doing is we are scaling from this point here up to this point here. It's a scaling operation, right? Same if we had an angle here, it would scale up to here. So what we really want to do is we want to take this result and we want to scale it by some factor. What is the factor? Well, our unit circle is 1, and our target circle here is 2, which is twice as much as 1. So we'd want to scale this by 2. So if we did 2 cos phi, 2 sine phi, we would get the point on the non-unit circle. And the same idea if the non-unit circle had a radius of 0.5. If radius equals 0.5, then you would be 0.5 cos phi, comma, 0.5 sine phi. So, in general, if you want to get the point on any circle, given the angle, it's just r cos theta, r sine theta. And that's all it is. Now we'll give you the point on any circle centered at the origin given an angle. Now up until now we've been looking at sine and cos in terms of a line drawn from the origin that has an angle and the intersection of that line with a circle. And sine and cos gives us the coordinates of that intersection point. Let's take a look at it from a different point of view. Same concept, different idea. So let's say we start with a point that's on the positive x-axis and on the circle. And we want to rotate that point by some angle theta. What are the coordinates of that point after the rotation? Well, we draw a little diagram here and we see, oh, it's just the same thing we've been doing this whole goddamn time. If you want to rotate a point that starts on the positive x-axis, all you got to do is it's just r cos theta, r sine theta. And that will allow you to rotate a point that starts on the positive x-axis. Here, r is just going to be the actual coordinate of that point on the x-axis. This is r. Now, with this information in hand, we can finally go back and analyze the code that I shown you before. I'm talking about this code here, the code used to generate the model for the star. So let's take a look at a basic 4-pointed star here. We can notice a whole bunch of things about this. First off, the number of points, or the flares, of the star. how does that relate to the number of vertices in the model? Well, each flare requires 2 vertices, 1, 2, 1, 2, 1, 2, and 1, 2. So the number of vertices in V is equal to NF times 2. That's the first thing we notice. Now the second thing we notice is that half of the vertices lie on one circle. The other half of the vertices lie on another circle. So the points are alternating between points on 2 different circles of 2 different radiuses. And we should also notice that the angles here between the points, between one point and the next point, it's always the same angle, right? And that angle is just going to be the entire circle divided by the number of vertices we have. So we can say theta is equal to 2 pi divided by the number of vertices. So what we really want to do here is we want to create a loop that will loop along these vertices and generate them. And the loop, we're basically going to run from 0 to NV minus 1. And what we're going to do, so we'll say I, it goes from 0 to NV minus 1. And for every I, our angle at that position, let's say that this is I equal to 1. Then our angle at that position, we'll call that phi. And phi is just equal to I times theta. That gives us our angle. Then all we're going to do is we're going to alternate. So for if I is even, we are going to do big R cos theta, big R sine theta. This is big R. And if it's odd, we're going to do little r. And alternating between those two, using sine and cos, looping through I, generating our angles, generating our points. And then you've got your star. And that's all we're doing here. We create the container for the star points. We know how many points we're going to have, vertices. That's just the number of flares times 2. So we reserve that space. D theta, which is our theta value, is just going to be 2 pi divided by the number of vertices, which is number of flares times 2. And then we're going to loop from I is equal to 0 to the number of vertices, which is n flares times 2. And we calculate the radius. Then we determine whether we're an even or an odd. And for even, we select the outer radius. If we're odd, we select the inner radius. And then we just do radius times cos of I times d theta. And there you go. That will generate your star. Procedurally generated star. Not super complicated once you understand the functions of sine and cos. All right, now let's wrap up our discussion of trigonometry with a little coverage on the good old friend Sohcahtoa. This guy, you probably heard about him if you've gone through, some kind of junior high school education system. It's going to be taught to you, right? So what are these and how does it relate to all the stuff that I've just taught you? Well, Sohcahtoa is it's a mnemonic for memorizing some formulas that allow you to solve for the parts of a right-angled triangle. So given a right-angled triangle where one of the angles is 90 degrees, if you have an angle and at least one side, so if you know that you have a right-angled triangle, you know one angle, you know one side, you can solve for all the angles and all the sides of the triangle using Sohcahtoa. So what is Sohcahtoa? Well, it's just a mnemonic that allows you to memorize these 3 formulas here. Sine theta is equal to opposite over hypotenuse, cos theta is equal to adjacent over hypotenuse, and tan theta is equal to opposite over adjacent. So the hypotenuse is always going to be the side that is opposite of the right angle. And then the adjacent, we say that if we've got an angle theta that you know, adjacent is the side that is adjacent to that angle, and opposite, let's call it A there, and opposite is the side that is opposite to that angle. So given these definitions, these formulas will hold true for any right-angled triangle. Now, forget about tan. Who told you to come here? I told you already, nobody wants to see you. Go away. You're not invited. Now, it's easy to understand the derivation of these guys if we go back to the context of our unit circle. Because let's just bring this guy over here, overlay him on top of the unit circle. And you can see here that if the hypotenuse is of length of 1, you draw a line down here. Adjacent is just going to be the x cos theta, right? Cos theta is equal to adjacent over hypotenuse. And hypotenuse is 1, so you're just dividing by 1. And opposite is going to be sine theta divided by 1. Hypotenuse is 1 again. So it just comes from the unit circle. And of course, the divide by hypotenuse, well, let's take it in the other direction. Let's say we've got a non-unit circle now. It's got a radius of 2. So we know that on this non-unit circle, the y, which is the opposite, is going to be equal to the radius times sine theta. And we know that the adjacent is going to be equal to the radius times cos theta. Now the radius is just the length of the hypotenuse. So we can replace this with h. And then if we divide by h, we see that sine theta is equal to opposite over hypotenuse, and cos theta is equal to adjacent over hypotenuse. So it all just fits together with what I've been telling you. The Sohcahtoa, they're all derived from the circle definition of sine and cos. But they can be useful for solving certain problems that don't line up to our standard position here. Solving certain problems involving angles, it is sometimes useful to think of them in terms of Sohcahtoa, instead of thinking of them in terms of an angle being rotated from the positive x-axis. And you'll see that a little later in this tutorial. We'll be making use of the Sohcahtoa, or at least the Sohca, because no one cares about the Toa. You go away. No one loves you. You were adopted. Alright, so we've learned a bunch about angles, about trigonometry, about circles, and we can see how that relates to rotation because we can use it to rotate any point on the positive x-axis. But in general, our points aren't going to all nicely line up on the positive x-axis. They're going to be, all over the gosh darn place, and we want to rotate those bad boys to other places using an angle. So how do we rotate an arbitrary point with an arbitrary angle? And that is exactly what we're going to do in the next video. I'm going to show you not one, not two, but 3 different derivations for the rotation formula. It's one of the most important pieces of mathematics for gaming and for graphics, and it just deserves the extra TLC. Until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more advanced C++.